So you have a increasing sequence, so it looks like this one. But at the same time, you have an upper bound. Okay, so somehow you have a ceiling that you cannot pass on, right? So this says that the sequence must converge somehow, right? So because it keeps going up, so it can't going down. It can't go down, but somehow you're stuck with the ceiling. So you must the sequence must converge. Okay. And on the other hand, if you have monotone decreasing, but somehow you have a floor, means that you cannot go down below this floor. So this push the sequence to converge also. Okay, so let's write this down. Uh, it, monotone sequence. It that monotonically increasing sequence. As an upper bound. And prejudice. And you can replace this increasing by decreasing, but then you have a lower bound, so you have a floor. Okay, so let's see. All right, so let's do the example there. One would be not say easy, but you may question why do we need to do this one? Okay, so that's the one that we had yesterday. So AN is this one here. So n squared over 2 to the n, but for n starting from 3. Okay, so what does a sequence looks like? Well, the sequence looks like, let's see, for 3, this is 9 over 8, right? So bigger than 1. For n equals 4, you have 16 over 4, that's 16, that's 1. Right? N equals 5, you have 25 over 32. Okay, here you have 36 over 64, and that. Okay, so you're wondering whether the sequence converges. So the question is, whether it is converge or diverge. Okay, and if it converges, to what's the limit? If converge, find limit. Okay. Of course, you can You know, from previous sections, if you pretend this is to be a function, now you have polynomial on the top and you have exponential in the bottom. Okay, so they are large for n large. Okay, so large over large, so you can do L'Hopital. Okay, and we know that the exponential is much larger than than polynomial, so it must go to zero. Okay, so that's the basic idea, but we want to use that the uh, let me just take a note. uh, you see, okay, so in this case you pretend this is a function. Okay, okay, so this is the intuitions, but this is polynomial. This is exponential. You know that a polynomial much smaller than exponential. Okay, therefore this limit x. So they are both, so this large over large, but then exponential is much larger. So that's why this is small. Sorry, small in the sense of limit. That means zero. Okay, so that's why it converts to zero. Um, sequence converges to zero. Okay, but specifically we would like to do uh, bounded monotone using bounded monotone. Bounded monotone. So we will show that this is decreasing. So what's it called? N square over is decreasing and has in lower bound. Okay. Okay, lower bound is easy. Why? Because both are positive. So the ratio of positive numbers is also positive. So zero must be a lower bound. Easy because it is positive. Yes, that's the we meant to show is just a decreasing. Okay, so how to show decreasing? Well, one of the thing we show decreasing is by, let's see, compare the compute ratio. Okay, so we will it's done quite often later on. Compute this ratio. So when we compute ratio, decreasing should be an should be smaller. Sorry, an plus one should be smaller. So then should be less than one, right? Because it's decreasing. So an is smaller. Sorry, an is bigger than an plus one from the next one. So the ratio must be less than one. So this is what we would like to show. All right, so let's compute this one. So an plus one is an square over 2 to the n plus 1. Okay, and divide by an. An is just rewriting this. Okay, let's uh, simplify this. Square there, and you have cancellations here. So 2 to the n is 2 to the n, so remain just 2. So right. So you get over what, over 1/2. Okay, so then let's check n plus 1 n square. So this looks like, ah, let's see, n at least 3, right? So for 3, this looks like 4 over 3. Uh, what can you say about this one? The question is whether this is less than 2. Okay. Okay. So let's compute this one. So is that this is questions? Okay. So let's say n plus 1 square, that is n square plus 2n plus 1 over n square. Okay. And that is 1 plus 2 over n plus 1 over n square. Is this less than 2? Okay, so that is to say that we want to show that 2 over n plus 1 over n squared, 4 and bigger than 3, is less than 1. Okay, so just check this one here, this n over 3. So this questions. All right, so let's, I should say this one. Check this out. 2/3 plus, this is 1/9. 2/3 plus 1/9, right? That is 9. So this is 6 plus 1. 7/9 less than 1. Okay, right? So for n equals 4, equals 4, so 1/2 plus, okay, this is even smaller, right? So that is 16/8/8, less than 1. Okay, and you can keep going on here. Show that this is really less than 1. This is less than 1. So this is less than 2. Okay, so you know that this is, so we can The conclusion is this. Let's say 1. That means this is monotonically decreasing. Okay. So by monotone bounded monotone, theorem, uh, is the sequence square converges. Okay, but it doesn't say the limit is what limit is. It just say about the what do you call it, the whether it is converges or not. Okay, let me just another example. Pick something from a book, something that's not something that we really need this one to compute. This example is done rather differently from example 6, right? So it's the same. So let's do this one here. Something that's not really from 31 to 36. Okay. Let's do this one here. For example, then okay, let's do 34. So this 1 plus 1 over 2 factorial until 1 over n factorial. So we have a kind of complicated sequence. Okay. So an is 1 plus 1 over 2 factorial, 1 over 3 factorial until 1 over n factorial. Okay. So if you try to write down the sequence, the sequence looks like for n equals 1. So this 1, right? So for n equals 2, let me just write 1 plus 2 factorial. So that's when 1 plus 1 half. So A3 is 1 plus 1 half. All right, so all right. You see from here you have a recursion. Recursion meaning the how you express the next term from this term. So you see that n plus 1 is actually an, right? So just add this one. Okay, so that's why they just this plus 1 over 3 a1 a2 is correct, right? Plus 3 factorial. 3 factorial is 6. Okay, so this is what do we call this? 6, 9, 9, 10. Okay, a4 is plus 1 over 4 factorial. Okay, so you can compute 24 times 4, 4, 40, 41. But it's looking at the sequence, it's kind of complicated. So how do you know whether it is converges or not? Okay. Let me just note. Hard to see in pattern. Okay. So let's do this one here. Mm, let's observe that the an is, let's see, it's less than this one. Correctly, or just one by one. A2, for example, 1 plus 1 over 2 factorial. Okay, so this is 1 plus, okay, A3, for example, 1 plus 1 plus 1 over 3 factorial. Okay, so that is less than, uh, okay, so 1 plus, okay, this is less than, there, right? So you place this 3 by 2, making this larger. Okay, A4, what about A4? Well, you have, uh, this is 1 plus 1/2 plus, plus 1 over 4 factorial. This 4 factorial is 1, 2, 3, 4, right? So this is smaller than 1/2, 1/2, 1/2. Okay, so this is smaller than, there. You notice this one? And similarly, you get this one, 1 plus, okay. This is index 4. This is up to power 3. Index 3, this is power 2. Okay, so this is, there we go. All right. Okay, and so then this is easy. This is the sum of, well, let's do this one using, how you call this one? The summations formula. Um, okay, this is called a, if you recall in high school, this is what we call part of geometric sequence. What is geometric sequence? Well, this is something that looks like 1 plus r squared plus r cubed, Rn. Okay? For some r. R is, well, it can be anything. Okay? And remember the sum? Sum is just, let's see, um, say this is Sn. Okay, sum till n too. If you multiply by r, of course you get this one. Sorry, this square. You, yeah, and you have another term, right? And so you subtract them. Okay, so you subtract. Let's see, this is 1 plus r. you factor Sn out. See, a lot of terms just cancel out. This cancel, this cancel, this cancel. So you end up with just first and then subtract the last one. Okay, so you get this and the sum. Okay, so R is called ratio. Why is called R? Because this ratio. All right. So this AN in the sequence. Okay, AN is very less than uh, this is 1/2 there. So 1 minus over n plus 1 over 1 minus r minus 1/2. So 1/2. What was it? 2 there, actually. Okay. So you see that the sequence here, you keep adding something here. So it must be larger and larger. So it must be increasing. Okay. So you see, AN is increasing, but this is less than, well, this is less than, of course, this is less than 1. So this must be less than 2. Okay. Increasing by y is increasing. Keep adding positive number. This 1 over 2. Sorry, 1 over. Okay, so it's increasing. Now we know this is bounded by 2. Okay, and therefore, uh, this sequence converges by monotone bounded. Okay, so that's something that you uh, it keeps larger and larger because you keep adding something here, but it is still bounded. Okay. Right. Questions? So that's, I think that's the one of the most important thing from section about sequence. Okay, so that's okay. So let's do this one now. We Example 3. All right, so we have this sequence. So in this case, an is no, the expressions can call complicated. The because this is a summation from 1 to n. Okay, 1 plus k over n square times 1 over n. Okay, and the problem says that show that this converge to pi over 4. Right, so what in the mind, so we can get this pi over 4. Okay, so if you try to write this down, you even get more confused because it doesn't seem to have a nice pattern. Okay, but if you recall, this is a Riemann sum. So the key idea is an is a Riemann sum. The question is, what is the functions? Okay, what is the functions and the bound of the integral? Okay, all right, so let's see here. Let's rewrite this one. So this must be function. This is 1 over n. Okay. What would you like to see here? What we would like to have is this is f of x of k. All right. And this is the delta k x, the delta. So then later on, we would like to see if this is actually okay. So say this is particular. Okay. So which converts to, let's see, this is integral of f of x dx. Okay, so the question is find f, a, and b, the bound. Okay, so then this looks like the xk. So you can say this is the whole 1 plus k over n square is the xk, or you just say that's 1 over 1 plus xk square. Okay, so xk here, so xk here is just k over n. Okay, k over n. So k starts from 1 till n. So what this looks like? Well, it is this interval from 0 to 1. Right? So you divide this up by n subintervals, which is 1 over n, 2 over n, 3 over n, dot, 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 so this k over n. Okay, so that's just really, all right. If that's the case, then this should be the A, that should be the B. All right, so the conclusion is that, I should say sub-conclusions, right? This limit of the sum 1 over plus k over n square, okay, is that's integral. A is 0, 1, This is the function is 1 plus x squared and 1 over n is just dx. Okay, so we know this is the arctangent, like it, this one. Arctangent 0 is 0. Arctangent 1 is pi over 4. That's you get the pi over 4. Okay, questions? All right. Um, so next we would start with infinite series. Okay, this kind of the longer one. So let's stop here. Take a break for 5 minutes then. Okay. Okay. There's only two of you who couldn't do the second part yesterday. Others okay? Better take.
Sir, I was okay, but I had issues uploading that. So it might be slightly like 1 minute late.
Oh, okay, okay. Then that's okay. Where's the chat? All right. So let's restart our session. It turns out that um, say all of you get problem with the accessing second parts. Eventually did it. So far uh, I don't think we need to give any make up second part for the for you. Okay. All right. Um, uh, well, then how can we? It's recorded anyway. Just so that the recording is not that long.